Hello everyone, I'm Eugene Liu from Keystone Academy. This video aims to help people get a better understanding about some science knowledge behind springs, which is a kind of tool that many people use in their daily life. Springs are pretty normal in everyone's life, but have you thought about the relationship between the force of the spring and its extension? Did you understand what spring constant represents when you are using springs? How can springs be related with physical concepts, such as potential energy? Well, this video will elucidate how springs can be related with all these physical concepts, and I hope it will help to answer your question. As many of you have noticed in your life, more or less, if people sling two different hanging weights on the same spring respectively, the extension of the spring, meaning the length that the spring increases, will be larger when the weight is heavier. In 1660s, an English scientist named Robert Hooke discovered similar physical phenomena and brought up the Hooke's law. Hooke's law is a law of physics that states that the force needed to extend or compress a spring by some distance x scales linearly with respect to the distance. The equation of Hooke's law is F spring equals to negative k times delta x. In this equation, F spring refers to the restorative force that the spring has. Negative k is the constant that describes the nature of spring, and delta x is the extension of springs. As you can see from the equation, the restorative force of the spring is proportional to the extension of spring, and by rearranging the equation, we can infer the constant of the spring if we are given the extension and the restorative force. So now you might be a little bit confused. Is this equation real? How does the equation need to multiply a negative k? And what is the restorative force? One thing I will need to clarify here is the F spring. It is the restorative force opposite to the pulling force that hanging weights exert on the spring. Here, I'm going to use one small experiment to help you understand this law better. Now, as you can see, there are two springs in different colors. What's more, there is a set of hanging weights that will sling to the free end of the spring later. In this short experiment, we are going to test their spring constant respectively. Then I will connect them in two different patterns, which are series and parallel, and see whether the spring constant will change. Throughout the experiment, I will use 4 different hanging weights. Their weights are 100, 150, 200, 250, and 300 grams respectively. I will repeat each group for 3 times, and later I will also evaluate this uncertainty for you. So here is the experiment. The following pictures are all the pictures that I took for the springs that I used during the experiment, and for each spring, its extension has been labeled by me on the screen so that you can see it, and the unit of the extension have all been converted into meters so that you can see it clearly. Now, I will insert the data I just got from the experiment to an Excel sheet, and here it is. As you can see, the data shows a linear relationship since the R value for each one is very close to 1, and I can say that the result on the graph is quite believable. According to the parameter given by the producer of springs, the red one has a spring constant of about 25 Newton per meter, and the white spring has a constant of about 40 Newton per meter. The N value calculated for my experiment for the red spring is approximately 34 Newton per meter, and for the white spring is roughly 46, which was not very accurate to the theoretical value, but still be able to prove the degrees of applicable of Hooke's law. As for series and parallel, the producer didn't mark the value for the N value on the box, but there are equations to describe the property of series and parallel springs on the internet. According to data noted about spring constant, the theoretical value for series should be about 25, whereas the theoretical value for the parallel is about 103. Well, based on the actual value I get from the experiment, I can make a chart like the one like this. So the percentage error for the theoretical value for the k value for the series is about 20%, and for the parallel is about 18 or 19%. And there is a nuance between the k values for both parallel and the series, but both of them exist within a reasonable range, for which the percent error of the series is about 16 and the parallel is about 18. The difference can be counted by the rust on the hanging weight, but generally speaking, the actual data fits pretty well with the theoretical data, which thereby proving the validity of Hooke's law and the law describing series and parallel spring. Now we will move to the last section of this video, the elastic potential energy. Potential energy is the energy possessed by a body by virtue of its position relative to others, stresses within itself, electric charge, and other factors. So, the elastic potential energy will be the potential energy of elastic objects, such as the spring that we experimented today. In today's experiments, we can notice the transformation between the elastic potential energy and the kinetic energy. Every time when I drag the spring, its potential energy will change, and when I release the spring, the elastic potential energy it owns will transform into kinetic energy. As you may notice in your daily life, elastic potential energy is everywhere. We can say that the place where the spring exists, elastic potential energy will definitely exist as well. Okay, so this is the end of this video. Today we talk about the Hooke's law and use the series and parallel experiment to prove its validness. We also explore how extension and force of spring can be connected with the work done by the spring. Lastly, we mentioned the transformation between elastic potential energy and kinetic energy. If you find this video be helpful, that would be great. But if you still have problems or questions, you can email me. My email address is at the end of this video.